So today we're going to start to look at the physics of rotating rigid objects. So think of bicycle tyres or car tyres or gears, or even things like rotating cylinders. So whenever we're dealing with equations in physics that deal with rotation, we must express our angles in units of radians rather than degrees. If we've got a circle here where the origin is in the centre and we decide to rotate it anti-clockwise by 180 degrees, so after some time delta t, it points in this direction. So the angle that it's rotated by is 180 degrees, but we can also say that we've rotated it a positive pi radians. And let's say we continue to rotate this another 180 degrees. So it completes one full circle. So in degrees, this would be 360 degrees. But in radians, this would be 2 pi radians. If instead we rotated it clockwise instead of anti-clockwise, these values would be negative. So counterclockwise, we have a positive change in angle, and clockwise, we have a negative change in angle. But this radian value, so this theta value here in radians, comes from this fraction. So we have some arc length here, s, divided by the radius to that arc. And these are both units of length. So the distance s represents how far we've rotated our rigid object about some fixed origin here. And r, the radius, is the distance from the origin to a hypothetical particle on our rigid object that sweeps out this arc of length s. So we could have a very large object here, and we could have a particle in the center or halfway between the origin and the outside of the object, and we could have a second particle out here with a different arc length. So we call that s prime, and this total distance here we'll call r prime. But the angle is still the same in radians. So if we sweep out an arc that has the same length as the radius, we get a value of unity. So for example, let's say we sweep out an arc length of 10 centimeters and the distance to that arc is another 10 centimeters. Then that equals 1. And that's the angle in radians that we've swept out, that we've rotated. Now, because the circumference of a circle is 2 pi r, then from this equation here, we can see that 360 degrees, or one full rotation, corresponds to an angle in radians of the arc length, so s, which is 2 pi r, which is the distance of one full rotation, divided by the radius of that circle. And we can cancel out the radius here, leaving us with 2 pi. And this corresponds with an angle of 360 degrees. Now we can convert any angle in degrees into radians using a conversion factor. And the conversion factor is pi over 180 degrees. So let's say we rotate this circle by, let's say, 45 degrees counterclockwise. If we want to convert 45 degrees into radians, then we just multiply 45 degrees by this conversion factor to give us the degrees, to give us the angle in radians. So pi divided by 180 multiplied by 45 will give us the angle in radians. So we got 0.779 to two significant figures. 0.79. So that's 0.79 radians to two significant figures. Now, because we're dealing with rigid objects here, where all the atoms that make up this object are fixed in place, we can associate this rotational angle with the entire rigid object as well as the individual particle and atom. Now, this is a bit confusing, but it makes more sense when we're dealing with the speed at which our rigid object is rotating, as well as the acceleration of this rotation. So, for example, we've got two particles here on this circle. In a minute, you'll see that their angular speeds are exactly the same, but their linear velocities are different. So let me try and explain this a bit more clearly. So we've got a rotating object here, and we've got two particles on this rotating object, which we'll call A and B. Now, they're both rotated counterclockwise by an angle of theta. So they undergo the same angle of rotation about a fixed axis here. We can say that the particles at A and B trace out different arc lengths, and therefore, if the circle is rotating counterclockwise, A and B will have different linear speeds, where B is going to be moving faster than A. But A and B have exactly the same angular speed. Now, the average angular speed, which is written like this, omega with a bar on top, is equal to the ratio of the angular displacement to the time interval during which the rotation occurs. So, which is the final angle minus the initial angle divided by the final time minus the initial time. And that's delta angle divided by delta t. So it's the speed at which this rigid object is rotating, and it has units of radians per second. And because radians doesn't have any SI units, it's just a number, it can also be written as seconds to the minus 1. And if we want the instantaneous angular speed, we define it as the limit of the ratio of delta theta over delta t as delta t approaches 0. So we write it like this. So the angular speed, or the instantaneous angular speed, is equal to the limit of the ratio of the angle over delta t, where delta t approaches 0, and this is equal to delta theta over delta t. And we're going to use integration in a minute to derive the kinematic equations for rotational objects, rigid rotational objects. So when we've got a positive angular speed, this is when the rigid object is moving counterclockwise, but we get a negative angular speed if our rotational object is moving clockwise. Now you probably see why this angular speed definition wouldn't work on rotating objects that are flexible or soft, like pieces of rubber, or say if you have a rigid object that has been heated close to its melting point. This equation here wouldn't work. And it wouldn't work because if we've got a rotating object that's moving counterclockwise and it's fairly pliable, then if we've got the origin at the center here and we start off at this position here and we're rotating counterclockwise, then a particle at A in the middle here might rotate at a larger angle then a particle on the outside of this object. So the material, or the atoms, closer to the origin, as this is spinning, may spin faster than the particles on the outside. And if this is the case, then we cannot say that the angular velocity or the angular speed is the same for all particles within this object. If it's rigid, then all particles sweep out the same angle as they're rotated. Now, you'll often see angular speeds as a vector, which we call the angular velocity. So if we're having a look at a rotating disk again, and it's on its side, then if this disk is rotating counterclockwise, then the angular velocity vector will point in the upward direction. If it's rotating clockwise, then the angular velocity vector will point downwards. And we can use something called the right-hand rule to determine the direction of this angular velocity vector. This is my really bad drawing of a hand. And if you imagine that the fingers are wrapped in the direction of the rotation, the thumb will point in the direction of the angular velocity vector. So when the fingers wrap in a counterclockwise direction, then the angular velocity vector points upwards. And the magnitude of this angular velocity vector will be positive in this direction, so this will be positive. If it's pointing in this direction when the object is moving clockwise, then the angular speed will be negative. So these rigid objects also change their rotational angular speeds over time. So we've also got the instantaneous angular acceleration. So think of like when you're driving your car, instead of moving at a constant velocity, you decide to step on the accelerator and speed up. The wheel's angular acceleration will also be a positive value, and their angular velocities will also increase. So we write the angular acceleration like this. So alpha is equal to the limit of the ratio of the change in the angular speed divided by the change in time as delta t approaches 0, which is equal to delta omega over delta time. And the angular acceleration has units of radians per second squared, or simply second to the minus 2. And much of this is analogous to all the things you would have learned in one-dimensional kinematics. So this would be equivalent to the acceleration of a particle along a one-dimensional line, where the acceleration would equal delta v over delta t. And I think it's really important to emphasize again that when a rigid object is rotating about a fixed axis, every particle on the object has the same angular position at a specific point in time. It will have the same angular speed and the same angular acceleration. But its linear speed and its linear acceleration will be different depending on where it is in the rigid object. So just to summarize, theta will give us the angular position of our rotating object. Omega will give us the angular speed of our rigid rotating object, and just put units up here. So the angular position is measured in radians, and we don't use degrees. Angular speed is radians per second, and alpha is the angular acceleration, which is in radians per second squared. Now we talked about the direction of the angular velocity vector. So if we're moving counterclockwise at a certain speed, then the angular velocity vector points in the upward direction. But what direction does the angular acceleration vector point when we're accelerating in the counterclockwise direction? Well, it points in the same direction, so it also points in the upward direction. If our rotating object moving in a counterclockwise direction is slowing down, then this angular acceleration vector will point in the opposite direction. So if we have something like this, a diagram like this, where you can see that it's moving in the counterclockwise direction, because we've got the angular velocity vector pointing upwards, if we also see that the angular acceleration vector is pointing down, then we know that this object is going to slow down. So let's try a quick question. Now we've got a rigid object here that is rotating with an angular speed of less than 0. So the angular speed is a negative quantity. So let's give it a number. Let's say it has a negative angular speed of negative 2 radians per second. The angular velocity vector and the angular acceleration vector are pointing in opposite directions. Okay, first of all, given the fact that the angular speed is negative, do you think that this rotating object is moving counterclockwise, so in this direction, or is it moving clockwise in this direction, given a negative angular speed? Well, when it's negative, the object is always moving in a clockwise direction, so it's moving in that direction. If it's moving in a clockwise direction, we know that the angular velocity vector will point down because of the right-hand grip rule. If we think of our fingers moving in the direction or pointing in the direction of the rotation of the object, then our thumb on our right hand will point downwards. Now, with this question that I've given you, I've told you that the angular acceleration vector points in the opposite direction. So that must mean that it's pointing upwards. So if they're in the opposite direction, what does that mean about the rate of change of speed of this rotating object? Is it going to speed up or is it going to slow down? Now, because the acceleration is opposite in direction to the angular velocity, this means that the object is going to slow down. It's almost like we're putting the brakes on this rotating object. So what we're going to do now is we're going to use all this information and start to derive the rotational kinematic equations for these types of rigid objects. In 1D kinematics, so I've got a course on 1D kinematics on this channel if you want to have a look, and I'll put a card in the corner at the top here. But in 1D kinematics, we found that there are 4 formulas that help us describe an object's linear motion when the object's acceleration is constant. And we can do the same with these rotating objects. And these rotating objects, we're going to assume that they can only have a constant angular acceleration. Now, in reality, a lot of objects will have a varying angular acceleration, but for these equations, we're restricted a bit. We're only allowed to use these equations when the angular acceleration is constant over time. It doesn't change. So the angular acceleration is the rate of change of the angular velocity over the change in time, and this will be constant for these equations. So if we rearrange this acceleration equation here and multiply both sides by delta t, so we've got delta omega is equal to the acceleration delta t, and what we can do is we can integrate both sides of the equation. So we've got the definite integral on this side of the equation between the initial speed of the rotating object, whatever that may be, and the final speed, and we can integrate between the initial time and the final time that we're accelerating this object. Now the acceleration is constant here, which means that we don't integrate it. We can move this outside of the integral sign, and we're only integrating delta t between time initial and time final. If we take the left-hand side and integrate that first, we've got the definite integral of delta omega. That equals the final speed minus the initial speed. And we also get something similar for the right-hand side. So we've got alpha delta t is equal to alpha multiplied by the final time minus the initial time. So what we've got is the final angular speed minus the initial angular speed is equal to the acceleration, angular acceleration, multiplied by the change in time. And this gives us our first kinematic equation for a constant acceleration, angular acceleration. And what we've done here is set our initial time to 0 seconds. So ti is equal to 0, and we get this formula here. So if we have a spinning object and we know its initial velocity, but if we know its acceleration and we know how long we're accelerating it for, we can work out the final velocity of this spinning object. So to get equation 2, we need to substitute this equation here, equation 1, into our equation for the instantaneous angular speed. And the instantaneous angular speed is equal to delta the angular position over delta t, time. So we can substitute the angular speed here into this final angular speed. So we can say delta angular position over delta t is equal to the initial angular speed plus the constant acceleration, angular acceleration, multiplied by the final time. Or we can simplify this to simply the time. If we multiply both sides by delta t, that will cancel out the delta t on the left-hand side, and we've got delta t on the right-hand side. And we can integrate both sides of the equation again. So if we integrate this side, the left-hand side, between the initial angular position and the final angular position, and we can integrate this side between the initial time and the final time, the left-hand side becomes the final position, angular position, minus the initial angular position, and then we integrate the angular speed here and the time. So we've got the integral between 0 seconds and the final, because we've set the initial time to 0, omega I, the initial angular speed, delta t, plus alpha, the angular velocity, and it's constant, so it's removed outside the integration sign, between time equals 0 to the final time, t delta t. And we can use the power rule in integration to integrate the right-hand side here. So again, we've got the change in the angular position is equal to the initial angular speed multiplied by t plus alpha t squared divided by 2, or t final squared divided by 2. And this gives us our second equation for kinematics. So let me write down the second equation in full. So we got the final angular position is equal to the initial angular position plus the initial angular speed multiplied by time plus half multiplied by the constant angular acceleration multiplied by the time it is accelerating squared. And with this, we can work out the final angular position of a rotating object in radians if we know its initial position, angular position, so if I've got a circle here, and let's say this initial position is equal to 0, if it's moving counterclockwise at a certain speed, omega initial, but it's also accelerating, so it's speeding up as it's moving counterclockwise, if we know how long it speeds up for, this time component here, then we know what the final position may be or will be. It could be over here, or if it completes many rotations, it could have a very large angular displacement. So for example, it could be 100 radians for the final position. In equation 3, if we rearrange equation 1, for example, to make the time the subject of this equation, and then insert this result into equation 2, we can eliminate time from our third equation. So let me just show you what I mean here. So we're going to rearrange equation 2. So the final angular speed minus the initial angular speed, we've moved this over to this side of the equation, and we've divided both sides of the equation by the angular acceleration, and we've got time isolated on the right hand side. Now we're going to plug the left hand side of the equation into the time variables in this second equation here. So let's do this. So we got the final angular position of our rigid rotating object is equal to our initial position plus the initial angular speed multiplied by this time term here. So we got the final angular speed minus the initial angular speed divided by the constant acceleration plus this half multiplied by the constant angular acceleration multiplied by time squared. So this term here squared. So we've got final minus initial divided by the constant angular acceleration squared. Now we need to simplify this. So I'm going to move the initial angular position onto the left hand side of the equation. So we got the final minus the initial angular positions is equal to the initial angular speed here, and we'll sort out this term in a minute. Final angular speed minus the initial angular speed divided by the constant acceleration plus half the angular acceleration, and we're going to square the numerator and the denominator of this term here, and this will simplify things for us in a second. Final angular speed minus the initial angular speed squared, and we have to square the denominator as well, so the angular acceleration squared. Now what we can do now is multiply both sides of the equation by 2 alpha, and that will help us eliminate this half term here and the alpha terms in this equation. We're simply trying to remove certain unhelpful variables in this side of the equation. So I'm going to multiply by 2 alpha. 2 alpha in front of this term here, and we've got 2 alpha in front of this term. So we can see in the numerator up here and the denominator, the alpha terms can cancel out. And the same is true for this term here. So we've got an alpha squared in the numerator at the top here. Alpha multiplied by alpha is alpha squared. And we've got an alpha squared in the denominator, so they cancel. And also the 2's cancel as well. We've got 2 divided by 2, which is 1. So they cancel. So if I erase the terms that we cancelled now, just to simplify this and make it more easier to view, all we need to do now is expand out these brackets and simplify the like terms. So let me do that. So I'm going to leave the left hand side of the equation alone, and I'm going to expand out the right hand side. So 2 initial 2 multiplied by the initial angular speed multiplied by the final angular speed, and we got minus 2 initial speed squared plus this term multiplied out. So we got plus the final speed squared minus 2 initial speed multiplied by the final speed plus the initial speed squared. Now we can cancel out like terms here. So we got this term minus this term, which will cancel, and this equals the final angular velocity squared, and we got 2 initial speeds here squared. So basically we're saying 1 minus 2 here, which is equal to minus 1. So we got minus the initial angular speed squared, and that's equal to 2 alpha multiplied by the change in the angular position. And we can rewrite this as the final angular speed squared is equal to the initial angular speed squared plus 2 multiplied by the constant acceleration, angular acceleration, multiplied by the change in the angular position of our rigid rotating object. So that's the third equation. And our fourth and final equation, instead of rearranging equation 1 to make t the subject, the time, we're going to rearrange equation 1 to make the acceleration the subject now. So the acceleration is equal to the final velocity minus the initial angular velocity divided by time. And then what we'll do with this is we'll insert this term back into equation 2 and simplify. Let me move that over there. So we've got the final angular position is equal to the initial angular position plus the initial angular speed multiplied by the time it's rotating, the length of time it's rotating, plus half of this value here, which is the final angular speed minus the initial angular speed divided by the time, multiplied by the time squared from here. Now 1 power of time cancels in the numerator up here and in the denominator. So I can erase some of this now. We can expand out this bracket. So we got half the final angular speed minus multiplied by time minus half the initial angular speed multiplied by time. And you can see these two terms here are the same. So we can simplify. We got one whole term here minus half of that term here. So 1 minus a half is a half. So we can simplify this, make that into a positive, and erase this term here. And then we can put these back into brackets. We can simplify and move the half and the t, the time, outside of the bracket. So we've got the final angular position is equal to the initial angular position plus half multiplied by the time multiplied by the difference in the angular speed. And that's the fourth and final equation. Now what we can do is use these equations to answer various questions so long as whatever rigid rotational object that we have, that its acceleration is constant. So let's do a couple of questions. And the first question, so we've got a wheel here that rotates at a constant angular acceleration of 3.50 radians per second squared. So we have alpha is equal to 3.50 radians per second squared. If the angular speed of the wheel is 2.00 radians per second and an initial time of 0, through what angular displacement does the wheel rotate in 2 seconds? So that would be our final. T final would equal 2.00 seconds. Our initial angular speed, omega initial, is equal to 2.00 radians per second. And we're being asked what the angular displacement after 2 seconds. So that would be the final angular displacement. And we can only assume that the initial angular displacement is 0. We can set that to 0. And our initial time, ti, is equal to 0 as well. So we need to find the angular displacement, the final angular displacement, given all these values here. Okay, so what equation here do you think would be best to answer part A of this question? So given our values here, I think this equation 2, would be the best one. So we got the final angular position is equal to the initial angular position, which is 0, plus the initial angular speed, and we were given 2 radians per second, 2.00 radians per second, multiplied by the time, which was 2 seconds, because it's moving over a course of 2 seconds, plus the half, the constant acceleration, that doesn't change over time, so 3.50 radians per second squared, and we're multiplying that by the time squared. So we got 2.00 seconds squared. The seconds units cancel out, leaving us with radians. The seconds unit here cancels out, leaving us with radians, which is what we should get on the left-hand side of the equation for the angular position. So when we sum this all up together, we get a final angular position in radians of 11.0 radians in the counterclockwise direction. Now we can use this up here to see how many times this has rotated counterclockwise. That's part B of the question. So part B asks us, through how many revolutions has the wheel turned during its time interval? So we're rotating anti-clockwise, and we've rotated by an angular position of 11 radians, and it's a positive value because we're moving counterclockwise. We can use conversion factor. So we know from what we said earlier in the video that 2 pi is equal to 360 degrees, which is 1 full rotation. So that will be our conversion factor. 1 revolution, or 360 degrees, is equal to 2 pi radians. They're both the same. So that's unity there. And we're multiplying it by 11.0 radians to get the number of revolutions here. Change in angle in terms of revolutions, complete revolutions, is equal to this sum here. And when we sum this up, we get 1.75 revolutions to 3 significant figures. So basically what we're saying here is this object over 2 seconds with a constant angular acceleration of this has rotated counterclockwise nearly 2 times. Okay, the final part of the question says what is the angular speed of the wheel at time is equal to 2 seconds. So what it's asking is what is this value here? So let's get our equations back. So what is our final angular speed when the final time is equal to 2.00 seconds? We already know that the final displacement is 11.0 radians counterclockwise. Our initial speed we've been given, so we know that omega initial is equal to 2.00 radians per second. What else do we have? We've got initial time, ti is equal to 0. We've got the angular acceleration, because that doesn't change, 3.50 radians per second squared. And we need to find this value here. So what equation should we use with all this information to get our final angular speed after 2 seconds? I think this equation 1, would be best, because we've got our final angular speed on this side and we've got all these terms here. So our final angular speed is equal to the initial angular speed at 2.00 radians per second, and we're adding that to the constant acceleration, 3.50 radians per second squared, and we're multiplying that by 2 seconds, our time, our final time here. so 2.00 seconds. And let's have a look at our units here. We need radians per second on both sides of the equation for every term here. So we've got radians per second here, which is fine. And when we cancel out the seconds unit here and 1 power of the seconds unit in this denominator here, we get radians per second here. Our equation is dimensionally correct. Summing that all together, we get 9.00 radians per second to 3 significant figures. So it's sped up. This is a positive value. Our rotational object is going counterclockwise and it's speeding up, and it's now moving at 9 radians per second. So we've got a simpler question now, which is calculate the angular speed of Earth's rotation on its axis. Is this term here, which is equal to the change in the angular position over time. So how can we work this out? This is equal to the change in the angular position over time, which is equal to 1 whole revolution over a course of a single day. So 1 revolution over 1 day is equal to 2 pi radians, because we want this in radians, divided by 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And this is equal to 7.27 times 10 to the minus 5 radians per second. And the final question we've got is, we've got a centrifuge in a medical laboratory that rotates at an angular speed of 3,600 revolutions per minute. And a revolution is 1 complete cycle or 1 complete circle, and we'll need to convert that into radians per second in a minute. This centrifuge is switched off and it rotates a further 50 revolutions before coming to rest. So we need to find out the constant angular acceleration of this centrifuge. We're going to have a negative angular acceleration because in effect we're starting off with a high angular velocity and we're ending up with a 0 angular velocity or a 0 angular speed, and we're going to have to decelerate this system in order to achieve that. So in other words, we're going to have a negative angular acceleration. So what do we do first? Let's convert this into radians per second, this angular speed. The initial angular speed is equal to 3,600 revolutions per minute, and we're going to need to use a conversion factor. So we've got 3,600 revolutions every minute, and we're going to need 2 conversion factors in fact. So first of all, I'm going to convert these revolutions into radians. Because we've got a revolution in the numerator here, we need to have revolutions in the denominator so that they both cancel out. So 1 revolution is equal to 360 degrees, but we can't work with degrees, so we're going to have to work with radians. So we've got 2 pi radians for every 1 revolution. So that will cancel out the revolutions here. But we need to convert this into seconds. How many seconds in a minute? So we've got minutes in the denominator now, so we need minutes in the numerator. We know that there's 1 minute for every 60 seconds. So the minutes terms now cancel out. So we end up with units of radians per second, which is what we want. We get a value after summing all this together, so 3,600 multiplied by 2 pi divided by 60, and our initial angular speed is 377 radians per second to 3 significant figures. We got our final angular speed of 0 because it's come to rest, and we need to deal with this 50 revolutions here. So what does this mean? So initially, our centrifuge will have a certain angle. It doesn't matter what the angle is, but we do know that the change in the angular position is going to be 50 revolutions. So it's going to cycle around 50 times before it finishes. So our change in the angular position is 50.0 revolutions multiplied by a conversion factor. And we know that there's 2 pi radians for every single revolution. And notice here that we've got revolutions in the numerator and denominator so that they can cancel out, leaving us with radians as our unit. 2 pi multiplied by 50 is equal to 314 radians to 3 significant figures. And this gives us our change in the angular position. And let's say that our initial angular position is equal to 0, so that this term can be our final angular position of 314 radians. And now we can choose a formula here, one of the rotational kinematics formulas, to solve our problem. The problem is asking us what the deceleration is, what the deceleration value is, or how fast it's slowing down. And we've only got these values here. So what equation is best if we want to find the angular acceleration? I would choose this one here, because we've got this value, the final speed. We've got the initial speed in radians per second. We want to find the angular acceleration, and we've got the difference in the distance it's travelled before it comes to rest. So I'm going to use this formula here. So we've got 0 on the left-hand side is equal to the initial angular speed, so 377 radians per second squared, plus 2 alpha, and the distance it's travelled, so 314 radians. We can rearrange this to make the acceleration the subject of the equation. So I've got here negative 377 radians per second squared divided by 2 multiplied by the distance 314 radians, and that's equal the negative on the outside, and that's equal to a negative 266 radians per second squared to 3 significant figures.